This problem is a very interesting problem posted by a student for a solution on LearnPick website, and thought this will be of interest to the students appearing for any competitive examination. Here I'll give you the solution. The problem is a small sleeve with the mass M is pulled with a constant force P up a straight smooth bar, which slopes the angle beta towards the horizontal plane. The length of the rod is B. The movement is slowed down by a spring with the spring constant K and the natural length C. Determine the force P so that the sleeve reaches the top position without speed when it started from rest in the bottom position. The whole system is in a vertical plane. The pulley is small. So this is the problem. So let us look at the diagram here. Here this is a sleeve. It starts from here, from rest, and it ends up here with no speed. And there is a force which is pulling it. And there are two forces which are acting. There is a force which is pulling it, and the spring force actually is opposing the motion of the sleeve. So initially, when the P force is greater, because when the spring is unstretched, the resistance from the spring is less. So this dominates, this force P dominates, and the sleeve accelerates. And after some time, they balance at some point, and then further as the sleeve moves up, the spring force will be more, because by that time it was stretched longer. The spring force would be more, and the deceleration will start. The result that it reaches the end with zero speed. So here, if you look at the state of the sleeve, we find the speed of the sleeve has not changed. It remained 0 here and 0 here. So the effect of the action of the force is basically to change the potential energy of the sleeve and of the spring. So we have to apply the law of conservation of energy. So the force which is doing the work for increasing the potential energy of the sleeve and the spring is this force P, and it is given that this is a smooth bar, so there is no friction, there are no losses because of movement along the bar. So what we have to do is the component of the force P along the bar is what is doing the work, and what is perpendicular to this won't be doing any work. So the work done by the force P, the work done by the component of the force P along the bar is doing the work, and that gives to increase in energy in the potential energy of the sleeve and potential energy of the spring. So let us just look at the energy that is stored by the potential energy stored by the sleeve. So here, so this is the bar, and this is a horizontal line. Then the sleeve rises by this height. This is the height by which the sleeve rises. So this is given to be angle beta. So this is angle beta. This is angle beta. Then this is height h, and the mass mg is what is the mass into the gravity, that is mg. H is the increase in potential energy of the mass, the sleeve. Now h we can get from beta, and this we know. The length of the bar is b, so we can get h. height, so we get mgh. Then the spring potential energy. This is first is potential energy of the sleeve. This is potential energy of the sleeve. Then the second one, the potential energy of the spring. Here the spring, so this is a bar. Then we have, this is the base of the system. Then we have the spring going like this. At the end it becomes like this. So this is given to be C. That is the natural length. That is initially before the spring is pulled up. This is the natural length is C, and this is B. So the stretched length of the spring is root B square plus C square. So the delta x which we have to take for so the increase in the length, the increase in the length is nothing but root B square plus C square minus C is the delta x. So this we can use, the stretched length is what gives rise to the increase in potential energy. If this is 0, then the potential energy increase 0. So this is the spring potential energy comes from this, and we have seen the potential energy of the sleeve, how to get. Then what is the work done? What is the component of the force? Here, the component, if this is say phi, P cos phi is a component of the force along this bar. So P cos phi integrate over dx. X goes from 0 to x. So this gives us the work done by the force, which is results in the energy in the spring and in the sleeve. So by working out this, then we can get the value for P. So I suggest the students, you please work out. Here you can just change the variable of integration from x to phi. So then you can do the integration. There is a relation between x and phi. You can see the relation is, for example, if this is phi, so we can see if this. So if that is phi, then we will have cot phi is equal to b minus x by d. Then we find minus dx is minus cosecant square phi d phi. So that makes our integration possible, and the capital X is nothing but this is B, the full length of the bar, that is B. So putting those values for capital X is B, and then the limits we can find out the integral, equating the integral. Integral is nothing but the work done, equating the integral to the potential energy of the spring plus potential energy of the sleeve. We can compute what should be P. So that solves the problem. Please work out the details. If you have any doubt, you please leave in the comments. I will respond to that. Thank you.